At the very front of logical headway is the European Committee for Atomic Research, CERN, prestigious for its pivotal commitments to molecular material science. As of late, the widely popular Molecular Material Science Research Center has uncovered an incredibly interesting finding from its Huge Hadron Collider that could totally change how we interpret the universe. Researchers believe these unusual discoveries could uncover the presence of outsider life in an alternate reality. This noteworthy thought has sparked energy and serious conversations among specialists. Could this amazing disclosure reshape how we might interpret the universe? Furthermore, once confirmed, what significant insights will this discovery offer into the nature of reality itself? Join us as we dive into the recently published discoveries, exploring how CERN researchers are ending their silence on this chilling new disclosure that has the potential to change everything we know. The European Organization for Nuclear Research, also called CERN, has been well known for its thrill-seeker tests since its origin in the 1950s. It has been in the spotlight several times for good reasons, but its examinations have also sparked concern about the potential creation of black holes, fractures in our reality, and numerous other dangers. One of CERN's most famous and controversial accomplishments was the development of the Large Hadron Collider, LHC. The LHC is the world's largest atom smasher, starting operations on September 10, 2008, and remains the latest addition to CERN's accelerator complex. Spanning more than 27 kilometers of superconducting magnets and a series of accelerating devices, the CERN supercollider cost more than $4.5 billion. Many would argue that this money was well spent, as the LHC has resulted in some of the most significant discoveries of the past few decades, such as the discovery of the Higgs boson and many other previously unknown particles. This enormous machine is capable of speeding various particles around the circle until they reach close to the speed of light, completing more than 11,000 laps. The LHC does this with a series of extremely strong electromagnets that generate a magnetic field inside the accelerator that is nearly 100 times more powerful than the field surrounding the Earth. Some have raised concerns about the effect of creating such strong magnetic fields on nearby gadgets, as well as its impact on the Earth's own magnetic field. Once these particles reach their maximum speed, multiple times the speed of light, particles heading in opposing directions are forced to meet in a violent crash, delivering tremendous energy and a variety of particles. When particles collide, a surge of particles escapes, with most of them lasting only fractions of a second before fading away. Changing the source of particles allows scientists to uncover new ones in this whirlwind, with extraordinarily sensitive detectors placed around the crash sites to record all the data from each collision. This massive influx of data requires a huge amount of time and effort to process. The LHC's investigations produce more than 15 petabytes of raw data from these crashes, which must be carefully filtered to extract the needed information. In 2017, the LHC reached a significant milestone by permanently storing over 200 petabytes of data in its tape libraries. To put this into perspective, 1 petabyte is equivalent to around 250,000 movies. But what exactly are they searching for in all this data? They identified something strange with a particular type of particle called the beauty quark. Quarks are the fundamental building blocks of matter and exist in various flavors, as defined by physicists. Some of these quark flavors are entirely unstable, decaying into different particles in the blink of an eye. The beauty quark, with an average lifespan of 1 in 1.2 trillionths of a second, became the center of attention due to a particular distortion. Its decay pattern differed from what researchers had expected based on the standard model. According to their expectations, when a beauty quark decays, it should be affected by the weak force and transform into a set of lighter particles known as leptons, either an electron or a muon. The standard model predicted a 50-50 chance for the two particles. However, the LHC data revealed that these quarks decayed into muons 70% of the time, as opposed to electrons. This divergence could exist if a previously unknown type of particle is involved in the process. This has led some scholars to speculate that new physics might be at play, and the discovery of a new force-carrying particle would imply entirely new physics that could extend the standard model and answer many confounding questions. The possibility of new physics challenges the standard model theory, which provides our best understanding of how the universe's particles behave. The Standard Model is a scientific framework that precisely explains every aspect of our understanding of the physical world's building blocks. The shocking thing is that despite this level of precision, physicists are well aware that the model is incomplete. The Standard Model only describes three fundamental forces: the electromagnetic force, strong force, and weak force. Currently, there is no representation of gravity, nor an explanation for dark matter, the universe's most prevalent form of matter. During recent experiments, scientists found an anomaly in the data they were analyzing that differed from the Standard Model's expectations. Although it is not uncommon to find results beyond this framework, given the volume of data produced by the LHC, this time something piqued scientists' interest, prompting further investigation. What might this new force be? To explain this unexpected discovery, scientists proposed the existence of a new fundamental particle, which they refer to as Z prime, a force-carrying particle. Although this force is the best bet, it is very weak, as no indications of it have been found so far. Researchers believe it could interact in a unique way with electrons and muons, but the extent of its interactions with Standard Model particles remains unclear for the time being. If researchers were to discover new force-carrying particles, it would be a long-awaited breakthrough in physics. Physicists believe that if this discovery is confirmed, it will help unravel well-established mysteries of the universe, making sense of problems such as dark matter and the role of the Higgs boson today. Some researchers believe that this unseen force could help fulfill one of physics' most significant objectives of the last century: binding together the fundamental forces of existence. According to Elon Musk, CERN built the largest and most powerful energy molecule collider in human history, the Large Hadron Collider, LHC. Between 1998 and 2008, more than 10,000 researchers from many institutions and labs across over 100 countries assisted with this process. The LHC sits within a 27 km long tunnel on the border between France and Switzerland, near Geneva, around 175 meters underground. The very first impact recorded at the LHC had an energy of 3.5 electron volts per beam, multiple times that of the previous world record. The energy eventually reached 6.5 electron volts per beam once the LHC was further improved. Musk noted that the LHC excels at proton beam collisions. Additionally, it can accelerate lead-on beams. Proton and lead collisions are typically conducted for 1 month to test the predictions of several particle physics theories. The primary goal of the Large Hadron Collider is to test the properties of the Higgs boson and search for a large array of new particles predicted by subatomic particle theories. Hadrons are composite subatomic particles made up of quarks, which are held together by a strong force, much like how particles and atoms are held together by the electromagnetic force. Protons and neutrons are two examples of hadrons, and many others, such as pions and kaons, were discovered in cosmic ray tests in the late 1940s and early 1950s. The LHC brings two colliding particle beams together so they can interact. The Higgs boson is thought to be a fundamental particle associated with the Higgs field. It is the quantum excitation of this field, much like how you notice waves in the ocean. The boson is like a new species in the particle zoo, lacking the quantum characteristics of key matter, as well as the carriers of quantum interactions like the electromagnetic force, weak force, and nuclear interactions. The Higgs boson was discovered at the Large Hadron Collider, a groundbreaking achievement accomplished by the two major multifunctional experiments, ATLAS and CMS. It was announced on July 4, 2012 at CERN. At the time, the new scalar boson was found mainly in two rare decay channels, providing the clearest signal: decay into a pair of photons, requiring an entirely quantum virtual process, and direct decay into a pair of Z bosons, the carrier of the neutral-weak interaction. Although the discovery of the Higgs boson established the Standard Model, investigations into this elusive particle did not end there. One of the main discoveries since 2012 was the confirmation of Higgs decay. According to CERN, the study of this elusive particle continues to evolve, particularly during the LHC's third cycle, especially once the accelerator's high luminosity upgrade is completed in 2029. This will allow the LHC to conduct more collisions, providing researchers with greater opportunities to detect strange physics, such as events that do not fit into the Standard Model. CERN estimates that when the accelerator is upgraded, it will produce 15 million of these particles each year, compared to the 3 million Higgs bosons produced in 2017. This may be helpful for identifying different kinds of Higgs boson theories that go beyond the standard model of particle physics, with up to 5 distinct types of Higgs bosons, some of which may be produced less frequently than the basic Higgs. Even before the enhancements, researchers have provided compelling evidence for a magnetic Higgs boson. But why does this matter? The Higgs field was enormously significant in the early times following the universe's creation. It dictates the very nature of the vacuum that exists in our spacetime. It allows matter and interactions to exist as we know them, as well as the development of mass in all known fundamental particles. Without the Higgs field and thus the Higgs boson, the universe would be devoid of any atomic components, stars, and life. This may help explain its blustering moniker as the God particle. Popular media helped cement the Higgs boson moniker after its discovery, most often traced back to Nobel Prize-winning scientist Leon Lederman, who, out of frustration, referred to the Higgs boson as the goddamn particle because it was so difficult to detect. According to Business Insider, when Lederman wrote a book about the Higgs boson in the 1990s, he wanted to title it the goddamn particle, but the publishers disagreed and changed it to the God particle. Aside from the clear need to describe the new particle, researchers continue to investigate the Higgs boson for 2 reasons. First, they need to understand how the physical vacuum we live in began in the early universe. Second, they need to understand how this physical vacuum can remain stable. The Higgs field is unique in that it sends non-zero mean expected potential energy to the physical vacuum, impacting our universe. Researchers believe that accessing the structure of this energy potential is responsible for the existence of electromagnetic force, with infinite reach and weak force with a very short range. To do this, scientists must explore how Higgs bosons interact with one another, and for that, they need to create pairs of Higgs bosons. The Higgs boson contributes to answering the fundamental question of how all other fundamental particles get their mass. However, its mass is yet to be explained. Any imbalance in the theory doesn't account for this mass, causing accidental instability. Quantum variations could disturb the vacuum itself, though this occurs on timescales much greater than the known lifespan of the universe. However, researchers are still searching for additional Higgs boson-like particles that would indicate the presence of new physics needed to settle the Higgs boson mass. All these considerations fuel the investigation of even more data and, if possible, access to greater collider energy. This is why, 10 years later, many scientists worldwide remain focused on this work. The Higgs boson was first proposed in 1964 and discovered in 2012. Scientists have questioned why it took so long. This is because the Higgs boson is both massive and incredibly unstable. To create such a massive particle, scientists needed to concentrate a tremendous amount of energy in a small container, requiring a high-energy collider. Once formed, Higgs particles disintegrate in a variety of ways, with only a small fraction detectable from the background. Researchers built the largest and most complex detectors to identify such particles, then analyzed billions of proton collisions to find a Higgs boson signature. Will CERN's operations and discoveries empower us to make huge disclosures? Will it send us to our ultimate end? Scholars have 3 main theories about what CERN is up to. The first and deadliest theory, which has made some point fingers at CERN, is that the organization is attempting to open a doorway to hell. Some believe that CERN's experiments with subatomic particles flying at the speed of light will propel humanity beyond the gates of the last hell. CERN's Large Hadron Collider, LHC, continues to be at the forefront of scientific exploration, pushing the boundaries of our understanding of the universe. Beyond its historical discoveries, such as the Higgs boson, the LHC remains a critical tool in probing some of the deepest mysteries of physics. As scientists collect more data, they aim to answer fundamental questions that have eluded researchers for centuries. The LHC's ability to simulate conditions similar to those just after the Big Bang is one of its most profound capabilities. By accelerating particles to nearly the speed of light and smashing them together, the LHC mimics the extreme environments in which the universe was formed. These high-energy collisions create a range of subatomic particles that scientists can study to understand the fundamental building blocks of matter. As we continue to explore the very nature of reality, CERN's experiments offer a glimpse into the deeper layers of the universe. The potential discovery of new particles or forces beyond the standard model could redefine the course of physics. One key area of research is dark matter. This mysterious substance, which is thought to make up most of the universe's mass, has yet to be directly detected. However, theories suggest that new particles might be the missing link in understanding dark matter. If the LHC uncovers any anomalies related to dark matter, it could have profound implications for our understanding of cosmology. In addition, the exploration of antimatter remains another avenue of intense research at CERN. Antimatter, the counterpart to normal matter, could unlock answers to why the universe is dominated by matter rather than antimatter. If this imbalance can be explained, it might solve one of the greatest puzzles in physics. As CERN moves into its next phase, with plans for upgrades and enhanced capabilities, the possibilities for groundbreaking discoveries are immense. The LHC's future experiments might not only answer long-standing questions, but also open doors to new scientific paradigms. Whether it's unraveling the mysteries of gravity, finding a unified theory of forces, or discovering entirely new dimensions of existence, the path forward promises to be just as transformative as the discoveries made so far.